All right, welcome. In this video, I want to continue to present some of the discrete math topics that we've been looking at. But now I do want to shift the subject matter that we're going to be talking about to more of a computer science focus. My expectation is that a lot of my audience are computer scientists or computer scientists in training, and so you might want to have subject matter that is more closely related to the programs that you might be learning to write as well. And so the pivot that we're going to make is we're not going to be talking about programs specifically, but we're going to be talking about something very closely related, something that you may encountered already in your other learning as well, which is the idea of an algorithm. And an algorithm is a very close, maybe a sibling of the idea of a program. Algorithms and programs go hand in hand. Another thing that goes hand in hand are problems and algorithms, and that's going to be what I want to focus on in this video, is what is a problem and what is an algorithm from the pure math or the discrete math perspective or from the computer science perspective. So before we jump right into problems and algorithms, I just want to bring out a few more definitions to again start filling in the field of mathematical topics that we can talk about, and again to set the stage for computer science topics. So in the last couple of videos, we've focused a little bit more on the notion of set theory. We've maybe written some proofs about sets, and we've introduced some of the basic set operations. Well, we can extend set theory now to what we might want to call list theory. As computer scientists, we think of things, we tend to package our data, at least initially, in lists. Lists is a common way to do that. Well, in mathematics, we don't really use the word list as often. That's a computer science term. In mathematics, we would use the word sequence usually. It depends on the topic at hand. There might be different words for this, but I'm going to introduce this word here, sequence, as an ordered set. And again, another word we sometimes might call these tuples, depending on what area of math we are operating in. Again, from a computer science perspective, sequences are maybe a little bit more what we see. So a sequence maybe highlights that we have different kinds of sequences or different kinds of lists that we might use in computer science, depending on what kind of data we're storing in that list or in that sequence. So for instance, we might, at least for the moment, focus only on numbers, and we could think of here as a sequence of numbers as being representing many different things. We might focus on it as a tuple if we were saying it represents maybe a point in some Euclidean space. Of course, a sequence of numbers could represent all kinds of interesting things, not just a point in some space. And so here again, we've just sort of abstracted that idea. So what am I saying a sequence is? I say here it's an ordered set. Let's just remind ourselves a set has a couple properties that are maybe important to highlight here because of the differences that a set has from a sequence. And I've got a couple of those differences right here. Here, since a sequence is an ordered set, the order that we place the elements in matters. And that's something that isn't true of a normal set. In a normal set, the order we place the elements in does not matter. We can rearrange them in any order and it's still going to be the same set. However, in a sequence, that is not going to be true. If we rearrange the order, we get a different sequence, even if they have all the same elements. And then another additional property that's true of sequences that are not true of sets are that we can allow duplicate elements, meaning for instance, the number 2 could show up more than once in the sequence, and where it shows up, its position in the sequence, again, is important, okay, to the sequence. We can't just reorder them without changing the sequence, but we now allow duplicate elements. Now remember, in set theory, we did not permit duplicate elements unless we were dealing with what we called a multi-set. In standard, straightforward sets, we do not permit duplicates. Of course, as I just mentioned, we do have a definition called a multi-set that would permit that in case we need to allow duplicates in our sets for whatever math that we happen to be doing with them. The last bit, maybe a difference that I haven't really highlighted yet, is that in sets we use curly braces, but in sequences we'll use round braces. And that's just how we indicate to our reader notationally that what we have here is a sequence, not a set, without having to mention it sort of verbally or in a more verbose manner to start out. Now I mentioned sometimes these are called tuples in math, following the formula here, sort of like double, triple, quadruple, quintuple, and so on. After a while, we run out of words. Around here is where most people sort of say, okay, I don't know what the next one is. I think it might be a hextuple, right? But at some point we just give up and stop calling them, they're sort of Greek or Latin derived words. We're going to just give them a number and call it an n-tuple. And so we could call it a two-tuple or a three-tuple, but usually we'll go back and call them doubles or triples. Doubles are also sometimes called pairs. But when we get up to maybe, if we have 10 elements, we might just call it a 10-tuple, or in general an n-tuple. And this here, these words, tuple and these other variants of it, tend to stress that the size of the sequence is sort of fixed. Like maybe we're talking about points in a two-dimensional space. Then all of the points will have 2 elements in it, exactly 2 elements, no more, no less. And so that is going to be maybe an extra criteria on the sequence beyond the normal definition that we have here, that it's just an ordered set. Here we place no requirement on the size of the set, so just like our normal sets, we could have any size from 0 to, well, any finite size, as long as we're restricting ourselves to finite sequences. Of course, we could also imagine infinite sequences. They're special, so sometimes we privilege them and place them in a separate category, but at least all finite sequences are permitted here. If we then want to limit them and say, no, all the sequences must be of length 2 for 2-dimensional points, or 3 for 3-dimensional points, or some other size for some other dimensional space that you want to represent points in, then you might be working with tuples instead of sequences. Now, in computer science, we're more used to having maybe a list that is dynamic in its size. It can grow or shrink. And so this mathematical definition follows that sort of pattern, that a sequence could grow or shrink. We could imagine adding things to sequences, taking things out, and so on. So again, I think I've probably really highlighted what a sequence is, but here are just a couple examples. The first one, these are 2 different sequences, even though they have the same members. Why? Because order matters. So these are not the same. Here again, we have a duplicate sequence. These are the first Fibonacci numbers, the first couple of Fibonacci, 6 Fibonacci numbers. Here, if these were sets, then the duplicate 1 doesn't matter. It's extraneous, it's redundant. We could eliminate it and get the same set. But with sequences, that's not true. The 2 ones here makes this a different and distinct sequence from the other one here. And then finally, I've just got another example of a sequence. This is a sequence that looks like of the powers of 2, and we could imagine extending this to an infinite sequence by just including all of the powers of 2 that come after. Of course, here I stopped at 2 to the 5th. Okay, there's another kind of sequence, of course, that's important to computer scientists, and those are strings. And so a string is really no different than a list of numbers, other than we treat it as a list of characters. And so from a mathematical perspective, there's really no difference there. However, when we start working with it and start thinking about problems related to strings, there are a couple extra properties about strings that are important. And one of those properties is that strings are usually strings of symbols. We usually call these characters. And these characters are selected from some set of characters that is, the acceptable set of characters. And so we usually name sets of characters alphabets. We call them alphabets. So a set of characters or symbols we'll call an alphabet. And then usually this is convention in automata theory, which is a branch of computer science. we'll often use capital Greek letters like sigma here, which is the sign, the Greek letter that we also use for the sum sign, right? And then here we have gamma, another Greek symbol, and these are the capital sigma and gamma that we will use for our alphabets. Now, the reason why we might use sigma for sums is because sigma S is for sum S, and same thing, the same reason we use it here for symbols is usually where we've pulled that out, and gamma is just our backup in case sigma is already being used, and that's again just the Greek sort of sigma gamma. It's just like going at ABC, sigma, gamma. We're just trying to pick other letters from the Greek alphabet that might represent an alphabet. Okay, so we're using symbols from the Greek alphabet to name other alphabets that we might describe. Now, here I've got an example of some of the different alphabets you might encounter, and here I've given them different names too. So my first one I called it sigma, and it's just A, B, C, D, E. I didn't fill them all in here, but we could have them all down to Z, right? 26 characters in this alphabet, which we normally call the Roman alphabet. And then we also have these characters, which are the Greek alphabet, which have different characters. Some of them correspond in ways. The Greek alphabet actually only has 24 characters, so there are a couple missing. And it has some, there are some that the Greek alphabet has that we don't have, and vice versa. Again, we often use these letters in mathematics to represent things. Sometimes we'll use these lowercase ones here for complex numbers, and we, as I already mentioned, we use the uppercase ones for certain things as well. Here's another example. We might use sigma sub 0, just using a subscript to give it a new name. And this is the binary alphabet. And the binary alphabet just has 2 elements in it, and we usually call them 0 and 1. And of course, this is a very important alphabet for computer science. If you need to store something in memory, you need to store it in memory in binary. And so you need to convert whatever it is you're trying to store into binary, meaning maybe you're trying to store strings of letters over this alphabet, but maybe it's an email message or something in a text message, but you want to store it in binary so you can send it over the internet or store it in a file. Then you need to store it in zeros and ones. Now, of course, that's something that we might focus on quite a bit, is translating or encoding in binary, and I'll probably say some more about that in a future video. The last one here is one that I've added as well, just of interest. This is the genetic alphabet. At least it's the genetic alphabet from a computer science perspective. If you are a biologist or a biochemist, then you have the type of training that you probably know what these letters stand for. And they stand in for certain biochemicals, I'm assuming, or enzymes or amino acids, or one of those biological words that that in my computer science perspective, I kind of lump them all together as kind of meaning similar things. I don't know what it is. Chemical goopiness. Why am I saying this doesn't matter to me? Well, because from a computer science perspective, these chemicals that together form DNA, what matters to us is that it encodes something. It encodes some kind of program, actually. The DNA encodes a program for doing something really interesting, which is creating a creature, a biological organism of some kind, which is a very special kind of program to be. The programs that we write in our machines don't often have the goal of creating and maintaining a living thing. Some of them do, but most of them don't. So it's a very special kind of weird program that genetics has encoded in our DNA. But the language that it encodes it in is the language of genetics. The language of DNA is encoded using 4 symbols, not 2 symbols like we would do in binary in our machine, which is sort of interesting and very cool, actually, from an encoding and an information processing perspective. We know, and in an earlier video, we did a little bit of translating numbers in different bases. Binary, because of, as I just mentioned, is the base that we would need for computers. Binary is very useful because it only uses two symbols, but because it only uses two symbols, it makes things kind of be a little bit long. And you probably noticed this if you've converted any numbers into binary, they tend to get quite a bit longer than writing them, say, in base 10. And that's why we would use octal or hexadecimal as alternatives to binary. It's a more compressed version. Now, I'm no biochemist and I'm no evolutionary, I don't know how evolution was working, but sometime during evolution, the creatures that were evolving had to decide what to write their DNA in. What language, what symbols should we use? Now, maybe out there somewhere there were some using a binary language. I don't know about this, maybe. But what we do know is that in the original life forms on Earth, the language that they used to start encoding their DNA used 4 symbols. And those 4 symbols were encoded as these chemicals. And again, I don't really even remember what the names of the chemicals are anymore. I read them in some genetics textbook 20 years ago. But my brain has just abstracted away those details, and that's a computer science trait. You take away the details that don't matter for the information processing task, and you let them go away. These things are actual chemicals that you could probably get in a test tube or something. I've never had to do that. I don't know what that is. All I need to know is there are 4 of them, and they have different names, and the names that we've given them are A, T, G, and C, but we could have given them different names if we wanted to. These are just the first letter of the actual chemical words that we name those chemical agents, but from my perspective, we might as well have just called them 0, 1, 2, and 3, because all it's encoding for me is a message of some kind. Okay, let's move on to that and take a look at, these were alphabets. Then why were we talking about alphabets? Well, we were wanting to build strings out of them. And so a string is just going to be a sequence, the definition we've already just looked at, applied to characters now. So it's just a special kind of sequence. And really, this definition here isn't doing anything for us other than setting up really an alias. We could just all the time say sequence of characters, but that gets a little bit tedious. So we're going to just say string when we mean sequence of characters. And so strings are again going to show up a lot in computer science, whereas they don't show up as much in normal math, just pure math, discrete math, but they are going to show up in our presentation because we want to look at maybe an algorithm that does something with strings. Okay, so that's where we're going to see. Now here, again, to signify strings, this is probably something you're already familiar with. We usually use quotes instead of the round braces that we would be using for our normal symbols. Again, notice that we actually use these curly braces for our sets, right? That's to signify these are sets. Order doesn't matter. Even though I've put them in this order, that's the conventional order, the order doesn't matter. I don't think this is the conventional order for the DNA. I think I just put them in that order. I don't know why I put them in that order. I just randomly put them down there. But again, order doesn't matter. But for sequences it does. We would use round braces to indicate that. But for strings we use quotes. Okay, so here I've got 2 strings. The first one here I call string, which is a string over our alphabet sigma here, the normal alphabet, our English alphabet. And then here I've got the string Gattaca, formed out of sigma D here. And that's, it's kind of an old movie now, but Gattaca is a movie about sort of genetics and genetic engineering. If you're interested, go check it out. And that's a string formed out of, over this alphabet. It could, for instance, one of the reasons they use the name Gattaca is because it's spelt completely out of these 4 characters. This could represent a gene, a very short gene. Genes are usually longer than this, but that could be a genetic sequence. How about that? Okay, a genetic sequence. Here I'm borrowing these now technical terms that we have defined to now express more technically what we mean when we're talking about a gene. A gene is a genetic sequence. Okay, that's probably enough warm up. Let's see if we can get into the next bit. Oh, I forgot one little important bit here. There is a special string. There's a special sequence, the empty sequence, but we don't usually have a special name for that. But the empty string is the string that has no characters in it, and we do usually give it a special name, which is, here we have the lowercase epsilon, that is. We also, what's the other, there's also sometimes we use lowercase delta as well, but epsilon is the one that I'm going to use here. So you might be out there and you might see a lowercase delta, which is sort of this weird ticky triangle like shape, but I'm going to be using epsilon for any time we need to represent the empty string. Okay, so like I said, we did a lot of warm up, but now we can maybe jump into the topic that I really want to talk about, which is problems and algorithms. So in computer science, a problem, or a computer science problem we might call an information processing problem, is going to be a relationship between the input and the output, or as I hear, the input to the problem and the correct output, the expected output. Now the important thing here is it's a relationship between the input and the output, so it really only tells us what the input is and what the output is, the expected output should be. It never tells us how to get there. That's why it's a problem. Okay, the problem is it's going to show us the input, what we should expect our input to be, a well-formed input. If it's not of this form, then we can just ignore it. If it is of this form, then this is the output we should be giving. Now, I've got here stated a specific problem, the minimum problem, which is a problem that you may have already faced if you've written some programs before. It's the problem of finding the minimum element in a sequence of integers for simplicity here. So to set us up, one of the important things in stating a problem in computer science and in mathematics is to try and state it as formally and precisely as possible. That means using the language of logic and mathematics, state the input and the output as precisely as possible. Okay? Our instinct is usually to describe these in natural language, that is English, and so what we're going to try and build up here is a little bit of a toolkit and intuition on how to formalize those informal problem statements. So the first thing here, let's again see how we formalize the problem statement for minimum. The input is going to be a sequence of integers, so there we're borrowing that mathematical definition we just looked at, what is a sequence, and of course integers was something we looked at in a previous video as well. So now that we rely on our mathematical definitions of what a sequence of integers are, and then this extra bit here is notation mostly. This is naming that sequence of integers, we're calling it A, and then also naming the integers in that sequence, A1 up to AN for some number n. Okay. Now here, I haven't said what n is, and really what we've done is we've kind of left that unstated, and which means there's an ambiguity here actually, that we try not to have ambiguity in our definitions, but here we have one. The ambiguity we leave here, we often will leave an ambiguity in when to disambiguate it, we have the obvious route, which is in this case, if we don't tell you otherwise what n is, well then n could be anything that makes sense. And in this case, n could be anything, well, let's consider what values of n make sense, okay? At least on the surface. First of all, could n be 1? Well, the way I've written it here, it implies that there is a second one, but that is not what's being implied here. It's possible n could be 1 if this list only had one element in it, it would just be the element A1. That would technically be a correct list satisfying this definition. We haven't said what the value of n is. Could n also be 2? Sure, we could end the list right here. Could n be 3 or 4 or 5 or anything greater than 2? Yeah, it could be. That's what the ... and the n here is trying to argue, is that we could have any n. Now, could n be infinite? That doesn't seem what's implied here. If we want something to be infinite, we don't have the last element here, the an. Okay, we might just have written it a1, a2, ... and then just close off the sequence. That's saying there is no last one. It goes on forever. But that's not what we're saying with this expression. This one's saying a1, a2, ... an. There is a last one, the nth one. Okay, but we still haven't said what n is, and that's where the ambiguity is. So I've said it makes sense that n could be any finite number so far greater than 0. What about 0? Could it be 0? Now, in general, for a sequence, yeah, remember the empty string had length 0. We could have an empty sequence. But for this problem, the minimum problem, now if we jump, it's when we get down to the output where things get important, where things change, or maybe change our perspective on this sequence, is that because we're looking for the minimum element in the sequence, if the sequence has no elements in it, that's sort of not a well-defined instance of the problem. It's not a well-defined input. Our input probably should have at least one element in it if we want to return the minimum, because there is no minimum of a list of 0 elements. So for that reason, I'm going to assume here that our n must be at least 1. Otherwise, we have no appropriate output. Now, if you want to say, hey, that doesn't make sense, you haven't stated that, so maybe someone is going to give us an empty list, then this version of the problem doesn't tell you what you should do with the empty list. It doesn't tell you what the appropriate output would be on the empty list. If you want to change this problem and do a slightly different one, closely related one, where there is some appropriate output for an empty list, maybe 0, maybe minus infinity, something like this. If that's the case, then we could redefine this problem. But the way that this problem is defined right now, the output has to be some element of the sequence. So this here, the output is saying return AI such that it is an element of the sequence. If the sequence doesn't have any elements, then it's impossible to return an AI. Okay, so that's a different case. But so assuming there is such an element to be returned, then what we're being asked to do here is return AI such that what? AI is less than or equal to AJ for all of the AJs in the sequence. Okay. Now here I'm saying less than or equal to all of the ones in the sequence. That's all of them, including AI itself. So AI we know must be equal to itself, and then less than or equal to all others. Now some of us might have an instinct here, shouldn't it be less than? Well, the reason I put less than equal to here is to cover a lot of interesting, weird, bizarre cases you might not be thinking about, okay? If all of our elements are unique, distinct, none of them are the same, then there's one specific minimum element, and we know that minimum element will be strictly less than all the other ones. So if there's n elements, it's less than n minus 1. But this definition, I've chosen to encode it in this way to allow it to also handle cases where there's going to be ties in the list, and then the worst case, or in our sequence or list, I'll use those names somewhat interchangeably. But there's also the possibility, the worst possible input we might get, it might not be that bad, but it definitely causes problems for this definition. What if all of the elements were the same? So let's say our list all just had a bunch of 1s in it. Well, then any one of those elements is the minimum element. They're all the minimum element, and any one of them is an acceptable output. And all of them would satisfy this condition of being less than or equal to all of the elements in the list. So that's how we know that any one would be an acceptable output. So even though when we normally think of this, we're thinking of a list of maybe all distinct or unique elements, here when we formalize a problem, we want to make sure it's as formal as possible and as general as possible, meaning applying to as many possible versions of this problem as we can. And so here I've tried to formalize it in a way that makes it, as I mentioned, as general as possible. Okay. All right, so I think for most of us, the minimum problem is not a very puzzling problem. In fact, it might have been one of the first problems you had to write a program for, and it's a simple loop. We probably know that. In a second, we'll take a look at that. But the other definition that I want to talk about here then is the other side of this. If we've just taken a moment to look at what a problem is, then how do we fill in the gap between the input and the output? The problem tells us where we start the input and where we end the output, but it doesn't tell us the route that we take to get there. That's the job of the algorithm. Now, this version of a definition of an algorithm is sort of for our standard straightforward algorithms. There are other versions of algorithms that might defy this definition here. Ones that come to mind are maybe parallel algorithms, quantum algorithms, a couple. They're algorithms that do satisfy this definition, but maybe have a few extra characteristics as well that are worth noting. But in general, the algorithm that you know is running on your machine is usually an algorithm of this type. Okay, so let's take a look here a little more closer. What is an algorithm according to this definition? It's a finite sequence of information processing steps. Let's piece that together. So first of all, an algorithm is a sequence. We've been talking about sequences already. Okay, information processing steps. This is something that I'm leaving vague. What does that mean? In your own mind, think of it as things like, you know, adding one variable to another, checking to see if a variable is bigger than 0, you know, looping. These are information processing steps, checks and assignments and so on. Okay, so an algorithm is a sequence of those steps. It's starting to make sense. When you write a program, we're kind of writing that sequence of steps down, right? It's a finite sequence of steps. Now, this one I might put a little asterisk by. Maybe we could permit infinite sequences. The problem with infinite algorithms, if we allowed them, is they take forever. And most of us don't have that amount of time to wait. So, you know, we'd want our answer sooner rather than later. So yeah, maybe I put a little asterisk on there, but a little one, a tiny one, saying there might be some reason someone somewhere wants to consider an infinite algorithm. Whereas the rest of us might only need to focus on finite ones. Okay, so an algorithm is a finite sequence of steps, and then what does it do for us? It transforms the input into the correct output. Okay, so the algorithm is a transformative thing. So we sometimes call this information processing. It processes the information, but I also like to think of it as transforming it. And this is specifically very clear when we start thinking about like sorting algorithms, where we start with a list in one order and then we transform it into a different list, a list in a different order. And so here we are changing or taking that input, the information stored in it, transforming it in some way, processing it in some way, and out comes the correct output for the problem. That's the goal of the algorithm. Okay, and so of course we say then that the algorithm solves the problem, okay, as long as it's correct. And so again, that's just sort of normal, the normal natural language way that we would speak about these mathematical objects as well. We would say an algorithm is for a problem or solves a problem, and then the problem itself, of course, never stipulates an algorithm. Now, why do we need to make this distinction? What some of us might say, well, okay, we got problems, and then we get an algorithm that's like a key in a hole, right? And that's true, except that the way that algorithms work is sometimes there's more than one key for that hole. There's more than one algorithm that will solve that problem. And of course, when we talk about sorting algorithms, something we'll do later on in this series, we'll see that, oh yeah, the problem of sorting is just one problem, but there are multiple algorithms that solve it, different keys that will fit in that hole and do the job for us, transform that input into the output, into the output that we want, maybe following different strategies along the way. Okay. I think, so these two concepts, problem and algorithm, are sort of the framework or the cornerstone that upon which we can build our understanding of algorithms and analysis of algorithms. Are our algorithms correct? Are they, how long do they take to run and so on? How much memory might they use? All of these are part of what we call algorithm analysis, and that's sort of a key important part of computer science is being able to look at your algorithm and understanding, is this correct? Is this efficient? Okay, so what about the minimum problem? Can we solve it? Do we have a solution for it? And you know, maybe if you want, if you haven't done this yet, you've probably done this if you've taken some introductory programming or you've tried to learn some programming on your own, making a little subroutine or a little procedure to find the minimum element in a list is pretty straightforward. And there's more than one way to do it, but there's sort of one way that most of us will come upon our first time, because there's a fairly straightforward and obvious way to do it. Well, let's attack this on an abstract level first. Let's tackle the problem. Maybe we're not writing a program to do this. Maybe we just have a deck of cards, or maybe we have a list of names or something that we're just trying to find the minimum element. How would we do that in an abstract way? Well, one thing we're going to need to do, we'll notice, is we're going to need to do comparisons, comparing elements to one another. And that's almost made very clear in our problem statement here. If we're going to find the one that is the AI that is less than or equal to all the other ones, then we have to do that by doing these comparisons. At least the obvious way that comes to mind is we might have to do comparisons. Okay. Further, if we find one, how are we going to be certain that it is the smallest? Well, it looks like we need to somehow compare it to all of them, either directly or indirectly. Okay, we need to compare it to all of them and confirm that it is less than all of them. So the route that we do this in usually is by keeping track of a minimum so far. So I've actually got some code here. This is what we call pseudocode, actually. This is code not written in any particular language, English you might say, but also it kind of looks like it's written in a programming language, but not one specific. It's not written in Java or Python or something like that. It's written in what we call pseudocode. Okay. Now let's just see what it is. So first of all, it's minimum's the name of the subroutine we're writing. It takes the input that is stated for the minimum problem, okay? And then it's going to carry out, it's going to use this loop with a little initialization to find the minimum element. Now, you don't have to believe me that this is correct so far, because I'm going to try and prove it's correct. Not in this video, in the next video. I'm going to try and prove it correct so that if you at least accept some basic premises about math, you should believe that this will return the minimum. But let's just see what it does first. Maybe you will agree that it's correct, but if not, we'll leave that proof off till the next video. So what does it do? Now, this is a common strategy, is we need to initialize this m variable here that we're using here is keeping track of the minimum so far, and we're going to see when we get to our proof that's exactly the role that it's placed on. When I say the minimum so far, it's the minimum of the elements that we've encountered and looked at and checked up to this point in the algorithm. So thus far, we're going to say, well, let's just look at the first element. And here's the simple bit. If there's only one element in the list, that element's the minimum. We're done. So if the list was only of size 1, we're done at this step. So that's why I initialize here with A1 as my first possible minimum. Then what we're going to do here is we're going to iterate through all the other elements, and we're going to compare each of those new elements to our current minimum so far. And if we find one that's less, we replace our current minimum so far. We update it. We give it a new value. Hopefully, our internal logical processors have already looked at this and said, oh, that makes sense. That means at the end, m will be the smallest one. And so at the end, we return m. And that's the goal here. Okay, so our goal here is to return m at the end. Now, as I mentioned for this algorithm, this is stated in a language we call pseudocode. Pseudocode means sort of code, maybe code, close to code, not quite code. Okay, and as I say here, pseudocode is a mix of natural language, which is what I'm speaking right now, and what we normally speak every day is natural language, and then code-like structures is what I say here. So we mix in things like a for loop or these list notations and the mathematical notations in there, sprinkling it in, turning it into something that looks like code, but whenever the code-like structures the implementation details get too onerous, we just sweep them under the rug and replace them with some natural language instead. Okay, and there's a lot of power we can put into there. So for instance, even though this algorithm is an algorithm to find the minimum, I can write a sentence very simply that says find the minimum of a list in natural language. That only takes a couple words, and if that's a step in the algorithm you're designing, instead of replacing those 5 or 6 words with this whole loop, you just say find the minimum in the list, and then replace it or do whatever you're going to do with it. And that's the power of pseudocode, is the ability with the natural language bits to capture a whole lot of maybe simple or obvious work in one sentence or expression that we can express to another researcher, another programmer, to inform them how we want them to code it without having to go into all the details of the implementation details of the actual structure. Something that we hope our listener, our audience can do for themselves. Okay. And then again, maybe that brings up sort of the important reason, why do we write in pseudocode? Why not write this in Java or Python or however I'm going to need it when I write it? The reason is the intended audience of pseudocode is not the machine. It is someone else. It's another human. And so the reason I write this is the easiest way to communicate to you, the other human, what the algorithm looks like, without having all the extra little details that we might have if we wrote, say, a Java program. Okay, like all the object framework and overhead that we need to put in place just to write a simple minimum algorithm like this inside Java is stuff that's just extraneous. We don't need that to express what the actual algorithm is. That's Java headache, not algorithm headache. Okay, and then of course, why do we put all that extra stuff in there in Java or Python or whatever language we're writing in? Is because the intended audience of the code is the computer. Here in 2020, we're actually at a stage where we're almost at the point where we can just tell our computer what we want it to do and it will do it, almost. But when it comes down to writing code, we're not there yet. The computers don't code themselves yet, so we have to write code in their language. We can't just come up to them and say, hey, machine, please write me an algorithm that solves this problem. We have to write the algorithm that solves the problem. And of course, that's maybe the reason why we're trying to study algorithms here. Okay, so that brings me sort of to the end of what I want to focus on. This video was intended to just bring us an introduction to what a problem is and what an algorithm is. So of course that's why I use the minimum algorithm, which is a very simple algorithm, one that hopefully all of us could have come up with on our own. It only takes that little bit of cleverness to do it. And so the following videos, in fact, series of videos, several videos, are going to be focusing on answering these 2 questions about an algorithm. Specifically this algorithm in the next video, but then other algorithms that we will write as well, which is the algorithm correct? Now, hopefully, as I mentioned, our internal brain compilers, our internal brain logical computers already looked at this and said, yeah, this is right. This works well, okay? Now, here's the problem with pseudocode, is it doesn't really have a debugger attached to it. What if I had an off by 1 error in my index? What if I wrote less than equal to here when I meant less than or strictly less than, and so on. These are little typos that sometimes our brain compiler and our brain interpreter is going to look at and say, oh yeah, that looks right, and then of course that's why we need to go and write the program and then run it, and when we press run and it crashes or whatever it does, we notice, oh yes, we did make those little errors, okay? So how do we know this is correct? This one is correct. Did I write any errors? Well, if we want to confirm it correct without trusting the machine as our debugger, right? We can instead write a proof. And that's what we're going to try and do in the next video, is write a proof that this algorithm is correct, that it will return the minimum if implemented the way that we describe here. Okay, so as long as you follow this algorithm, it will give you the right answer, no matter what language you implement it in. And again, that's sort of the second important reason why we communicate algorithms in pseudocode and not in a language is you, the listener now, who might want to write this minimum algorithm, might be writing it in Java or Python or BASIC or JavaScript or some other language. It doesn't matter. Maybe some bizarre language that doesn't even use sort of the standard straightforward structures like for loops. Maybe it only uses recursion. Then, you know, translating this into your language is going to be easier if it's stated at an abstract level, not with all the implementation details that you would have to undo and then redo to translate a Java program into a Python program, for instance. Okay, that's the sort of the first question is this correct? The second question then is this efficient? So the way that I've got that stated here is how many operations does it take to execute this given a specific input. Now, both of these questions are critical and important, but really, if you don't have a correct algorithm, there's not really a lot of point in asking if it's efficient or not. A incorrect algorithm is kind of just like a broken tool, it's useless. So we're going to focus first on correctness, but then once we've spent some time talking about correctness, we'll come back and also talk about operations. How much time, how efficient is this? Okay, so that's all I wanted to do for this video here. And in my next video, like I mentioned, we're going to prove this algorithm correct. So please join me in that next video. Thanks again for watching, and we'll see you in the next video.